and we're excited to welcome Dan Lambert, a process engineer and researcher at the Savannah River site. Dan brings 39 years of experience with a focus on chemical process improvements for stabilizing high-level radioactive waste in the Defense Waste Processing Facility near Aiken, South Carolina. His work includes efforts to eliminate flammable gas generation, improve anti-foam agent efficacy, and improve mercury recovery during radioactive waste processing. Dan's talk today is titled Mercury Recovery Challenges and Successes During Processing of High-Level Radioactive Waste in the Defense Waste Processing Facility. Dan, thank you so much for being here today, and the floor is yours.
Great, thank you. Let me go ahead and try to gain control here. Can everybody see my slides?
No.
It's blank.
So that's a no. Let me try a different way of sharing. Can you see anything now?
No, it looks like your camera's off or some, it's just saying DL for, we just have a blank screen.
Okay.
There you go.
So you're seeing all of my whole slide, all the slides on the screen?
We're seeing the main slide and then your next slide, your preview of your next slide.
So you're seeing the wrong.
Yeah.
And I'm actually only seeing a black screen, so I don't know if it has to do with the location of. Are Georgia Tech folks seeing the slides?
I'm seeing what Jody's seeing.
Yeah, I'm seeing it.
I am also seeing what Jody is seeing. Great. I'm just going to reboot.
Now we're just seeing the blank screen. Don't know what to
Yeah, it's
and
blank.
you've hit the share and
Okay.
Yeah, it should have been a swap views menu item that would have swapped from presenter mode to presentation mode when you had it originally, when it was showing.
You're still seeing a blank screen?
yes.
Yeah, we actually see your desktop now, the Teams window.
So you're seeing it now?
We're seeing your desktop.
My desktop, okay.
If you hit Control-Shift-E, what happens?
Control-Shift-E. So I have two screens, and one I'm seeing the slides on, the other one I'm not seeing is my preview screen. And you're not seeing either of those.
Can you move over to your other window? To your other.
I just tried to do that. I've swapped from. You're still not seeing it, right?
No.
Dan, is this something you could send Jody and she share it and you talk through it and ask her when to advance? Just as a thought.
It's a really
I
good
don't know if you-
idea. The
I don't know if you
answer
have to clear things or not.
is no, just because it's so big. I have some videos in it.
Got it.
So there's two choices I have here. I can share the screen, which is what I usually do when I present from afar. Are you seeing it yet?
No.
Still
Dan,
a
I've
blank
had
screen?
similar troubles when I have two screens.
Yeah. Let me see if I can set it up so both my screens show the same thing. Give me a second here.
There we
Oh,
go.
there you go.
Much better.
Success.
So what are you seeing?
We see your
Presentation
first
mode.
slide.
Title slide. Yep.
Are you
Yeah,
seeing
not
all
The
the
actual
slides?
presentation. Yeah,
Yes.
so this is
Yeah.
presentation mode. You had presenter mode before, where you showed both the next slide and the current.
Okay. So let me just go ahead and get started then. Sorry, this is taking so long. If you can see it, I'm just gonna
Yeah, you're in
page
edit
through
mode
these.
now.
Yeah,
we
but if
can
I
see
go,
it. So if you want to just go forward,
Yeah,
it's
just
okay.
go
We
from
can see
edit.
it.
You can like collapse the ribbon. You can collapse the left-hand side if you want to make it bigger. It's up to you. Forget what I said. Just go.
okay. So let me go back to my first slide. I'm going to talk about Mercury recovery. That's something I've been doing for about the last 5 years. Some of the challenges and successes in the facility I support, which is called the Defense Waste Processing Facility. I have me listed with my intern, Emma Brown. She did a lot of this work this summer for me. And I appreciate that, but I wanted to acknowledge her as I start. Just a little bit about me. I have a BS in chemical engineering from Ohio State. My wife's a nurse. I have 2 kids, Mike and Eric. They both have chemical engineering degrees from University of South Carolina. And one of my sons has a couple of kids, so now I have 2 very energetic grandsons. You can see the picture of us all in the upper right there, and also have 2 golden retrievers that
Dan, you're not showing the About Dan slide.
It didn't advance.
it's not advancing. Still showing the title slide.
Yeah, you're still
Yes.
in edit mode. So if you try to advance, you'd have to actually click on 2 to get it to advance.
Is it advancing now?
Did
I
you,
don't see it.
did you click on the second? Did you click on the second slide?
Yeah, it's showing on my screen. And I have the red bar or box around the screen as if I'm sharing it, but it's obviously not sharing. I'm going to exit out of PowerPoint and try to start over again. Just give me a second here. While things load back up again. But anyway, I was showing you a picture of my family. It's a wonderful picture. Especially the picture of the dogs there. So. It's just a big file, so it takes a minute to open up.
Dan, there's something you can click on that says present in Teams at the top of your screen.
of my screen.
All the way over to there.
Okay.
Yes, there it is.
We got it.
You got what?
Yay!
Your dogs and your family.
Yeah, but I'm not showing that on my screen, so. Let me see if I can go to the next
You
one.
know them all.
Can you see that it says Mercury 101?
No.
Mm-mm.
So you're stuck on my screen.
I'm wondering if it's some sort of input lag. Because I don't even see the cursor moving in the screen
Yeah.
share.
Okay. You see anything now?
Dan, I have the PDF that you sent me. Should I just include that, share that in the chat, and then people can click on it and follow?
Yeah, I've got it here too, so it just doesn't, yeah, if you can give me a second, I'll try to, it says I can't find the file on my computer, probably because I moved it. Let me see if I can open that. Are you seeing my opening the PDF file on your, can you see that?
Mm.
So I've opened it up in the same PDF that I sent you. Can you see that?
Yeah, I can just see on the screen what the first slide is.
Okay, good. That's what I have showing on my screen too, so.
Okay. What I can do, let me see if I can.
Can you see my second screen or slide now?
No, just the first slide.
So you're just seeing the PowerPoint stuff.
Yeah,
though.
that's PowerPoint because I see the notes section at the bottom. It's not a PDF.
Do you want me to put the PDF in the, oh, it's not, it won't let me put it in here. I think it's too big.
So, I mean, I have it open on my screen, but you say you're not seeing it.
Well, I was just going to put it in I was going to put the PDF in the chat. Oh, yeah, now I see it.
So now you see what?
I can see your files that say Adobe Acrobat and then the CREST ECP seminar.
Yeah. Yeah, I don't even know where you see that from because it's not showing on my computer. So can you see what's showing on my second screen?
It says,
We put science to work.
Okay, so you're not seeing the PDF file that I'm seeing on my computer.
I think I'm seeing part of the PDF file. It's just not completely loaded.
I mean, it's on my screen, it's showing the red box around how about if I leave the meeting and then rejoin and try this again? Can I
Okay, sure.
try restarting Teams and maybe
Okay,
something new will happen? I'll be right back. Sorry
okay.
about this.
It's okay.
My Teams is also possessed, so who knows?
Mine is also possessed, as is my Outlook on occasion.
We had a Zoom earlier. It actually worked. I don't know. I didn't know how to process that. Zoom doesn't normally work if I have the VPN on, and it finally worked for once.
Okay, let's hope this works for him.
So I have rejoined. Can you hear me?
I can.
Yes.
Try to share my screen. So
We
can you
can
see my screen?
Yes.
Mercury 101.
Okay. So let me go ahead and get into the talk if you don't mind. Just want to give you a little overview of mercury for those of you that don't know much about it. I think everybody knows it's a dense metal, density of about 13.6. It's one of two metals that are, or two atoms that are metals that are liquids at room temperature, bromine being the other. It's toxic. It's particularly dangerous. I think you know that. But there's a lot of things about mercury you probably don't know. Like it loves to hide in crevices and low places, and likes to vaporize when you don't want it to, and condense when you don't want it to. It can be steam stripped because it has a really low vapor pressure, but it's not zero, and that's how we remove it in our processing. It can also be condensed in a condenser. It's really hard to separate it in our facility from water, and it seems like it should be so easy because of its its density being 13.6 times higher than water. But it does certain things, like it likes itself better than water, so it can form a raft, it can form an emulsion, lots of things that keep you from actually separating the mercury from the water. And it's also pretty reactive. In our facility, we have acidic solutions with nitric acid, so they're pretty good at dissolving up the mercury. And you'll see some pictures later where things turn yellow. If the pH is too high with caustic, it's gonna oxidize. If there's air present, the oxygen is gonna oxidize it. So it's really easy to lose it by reacting it. And so to keep from losing it, we need to pump it out of the vessels that we collect it in. And all the mercury pumps are broken, so we can't do that. So I also was trying to show you a couple of images from periodic tables. On my periodic table here, mercury shows up being purple because it's a liquid, so I made it purple here. But if you look at the bottom right, I love when I search for things on the internet and they have really wrong information. Like this one shows the atomic number of mercury being 74 instead of 80, and it has the atomic weight being wrong too. So I just remind you just not to believe everything you read about mercury on the internet. Okay. So now that you know mercury is toxic, it's ranked 8th by the World Health Organization for chemicals of major public health concern. So that's a circle of all 8 of them. Kevin and I got to work with 2 of them, being benzene and mercury. And if you try to find mercury humor, there isn't very much of it around, but this is one that I did find that you might chortle at. But it says a hug without you is just toxic. If you take a U out of HUG, you get HG. So That's the really funny part of it. So in the defense waste processing facility, the mercury equipment used to work. We used to accumulate some mercury in the mercury decanter. We used to pump it from there to the mercury cell. In the mercury cell, they purified it to remove any radioactivity that might be there. And then the idea at one time was we're going to sell it to people who wanted formerly radioactive mercury. For some reason, they never found anybody to take it. But and we also noticed that it was accumulating in a tank that we didn't expect it to, which was this big condensate tank instead of the small mercury decanter. We've made lots of changes to processing through the years, and all these changes have made things worse as far as mercury recovery. So it's accumulating in the wrong tank. It's what we're hoping is it's low enough in radioactivity that we don't have to process it anymore, because this mercury processing cell has been, we say that it rocked up, it all solidified, doesn't work anymore. They don't have a crane that can fix it, and so it'll be a long time before it'll be back in service. So if we could just pump it out to the right place, maybe we could put it in some kind of a vessel and get somebody to take it from us is the hope. So the DWPF is a huge processing facility for handling high-level radioactive waste. And so far we've processed about 36 million gallons. There's two kinds of waste, something we call sludge, which is the insoluble solids, and the salt waste, which is the soluble solids. Most of the radioactivity is in the sludge waste, and that's mostly what we've processed through DWPF in the past, although we've just started up a new facility that allows us to process the salt much faster too. But we have about 35 million gallons of waste to process. The problem is to process it, you have to dilute it by about a factor of 3, so there's about 100 million gallons left. And if you believe the company that runs the facility, will all be done processing in about 10 years. I wouldn't bet on that though. So I was telling you that there's 2 tanks that are accumulating mercury right now. If you look at the top left graph here, that's showing you the mercury in the mercury decanter. And over a period of about 2 years, it went up by 2 gallons. Every batch, we should put another 3 gallons in. So in a year, it should go up by 50 gallons or so. But we are accumulating in another tank we didn't expect it to, which was another condensate tank. What we'd really like, if you look in the top right here, we'd like nice, shiny elemental mercury. The problem is we don't get nice, shiny elemental mercury. We get little tiny balls of mercury. In the experiment that we just did, the mercury actually looked black. It's such a fine nano-sized particle that it looks black instead of silver. And of course, what that means is it's got to agglomerate before you can collect it. So you can also see some bubbles that are coated by mercury here. That's another really good way to lose mercury, is if you can get it buoyant, it's going to leave the decanter from the top instead of the bottom, and you'll lose it. So we'll talk about some of the factors contributing to the poor mercury recovery, the nature of the mercury itself. The condenser and the decanter are really poorly designed vessels. We'll talk about the fact that the condensate collection tanks are way better decanter for mercury than the actual mercury decanter is, and some other process factors we've learned that might help us into getting the mercury to agglomerate faster. I went to the internet and I asked one of the artificial intelligence programs to put together a little animation for me to show you what happens when mercury vapor comes into a condenser. That's what I'm trying to show on the top right, where it's showing the mercury vapor coming into the condenser, and it's being condensed. The problem is there's about 2,600 moles of water that's coming in for every mole of mercury. So I told it to show me in red all the mercury droplets. And of course you can't see any because they're so there's so few of them that they don't show up in the image here. They slowly accumulate over time as we process for days and days and days. And eventually you get you can see the red mercury droplets collecting at the bottom of the vessel. But that's one of the reasons why it's so hard for us to remove the mercury, is because it's such a fine droplet, and if it doesn't agglomerate into a big droplet and drop to the bottom of the vessel, it's actually going to leave out the top of the decanter, and we'll lose it. So why does mercury recovery matter? Mercury actually causes problems in downstream facilities. Obviously, we don't want to release it through the stack, although we do with some of it right now. We're trying to minimize that. So that's one of the problems. But what we're doing right now is, instead of releasing it through the stack, we're releasing it through our recycle through the condensate. And what that means is the recycle gets in future batches. And so we're going to process it again another time. So what we're seeing is the mercury concentration is going up every single batch. We set a record in this particular sludge batch. We're up to the 10th sludge batch. And it's going to get higher every time if we don't start recovering the mercury and quit sending it back in the condensate. So it takes a lot of energy to remove the mercury. I told you we boil for days and days. It's about 4 days of boiling in one vessel that we call a shrat. There's 4 days of boiling in another vessel we call a SME. So in a particular batch, we're going to spend 8 days and 2 weeks just boiling water to remove the mercury. And obviously that's expensive. It's actually cheaper than using the melter as an evaporator, but it takes us about 750 pounds of steam to remove a pound of mercury. So it just takes a really long time because of its low vapor pressure. We'll talk a little bit about the mercury timeline, because in the last couple of years, we've actually improved mercury recovery. We started recovering in a second tank, which is our condensate tank. But there's 4 things we've done that have made things better. One is we've gone to new anafoam. This was one of my big projects for about 5 years before this. The old antifoam used to degrade into 3 flammable gases. And obviously you don't want flammable gases when you're processing high-level radioactive waste. So this has been a huge benefit for us. It's also allowed us to boil much harder because we don't have foaming problems anymore. We started up a facility called the Salt Waste Processing Facility, which is going to handle that 100 million gallons of salt waste that's left to process. But it's also bringing lots more radioactivity into the facility. Because we're bringing so much volume into the facility, we're boiling longer. So we don't need to boil any extra for the mercury anymore, because we spend so much time boiling off the liquid that brings the radioactive cesium stream into DWPF. One of the things that happened is there was a pump that supplied the liquid to the ammonia scrubbers. Kevin probably remembers this. We had a huge problem with both ammonia and hydrogen being 2 flammable gases that we discovered during the pilot testing, especially of the before we started up the Defense Waste Processing Facility. And so we installed ammonia scrubbers. We put much bigger air purges in to handle the hydrogen. And then the ammonia scrubber pump died, and they haven't fixed it in the last 6 years. So the ammonia scrubber pumps are off. But it turned out the ammonia scrubbers were really good filters for the elemental mercury. So one of the big reasons that we're recovering so much mercury now is because the pump's broken. And the last thing we did is we changed the processing. And in the olden days, we used formic acid to reduce the mercury to elemental mercury so we could strip it. We've changed to glycolic acid. And what that's done for us is it's eliminated this hydrogen generation we worried about. So we've decreased the purges. There's lots of things that are now improving the mercury recovery. So, but we've also spent a lot of time studying the mercury. And so I'm going to talk a little bit more about how we process it and how we it's really a 4-step process. You reduce it, you strip it, you condense it, and you coalesce it. And we'll talk about them kind of one at a time. But I told you the glycolic acid is used now for reducing the mercury. It comes in as an oxide, HGO, +2 mercury, and it's reduced to elemental mercury. Even though I have it listed there as HGO, that's elemental mercury. That's just a mistake. And once it is in its elemental form, it has a really low vapor pressure. You can see it's like 3 orders of magnitude lower than water, which is why we need about 750 pounds of water to remove a pound of mercury. If we reduce it, then we can strip it off, and we can condense it, we can coalesce it. And because of the nature of mercury, often you have a nice big mercury droplet, it stretches, breaks up into multiple droplets. When that happens, you can see that there's these really tiny droplets that form too. So instead of having this big pool of mercury like we would envision, we end up with lots of really small droplets that we lose from the decanting process. So I'll show you a little bit about what happens inside the decanter and one of the reasons why we're not recovering more of the mercury in the decanter. And that's because we need to measure the liquid level of mercury in the decanter. And to do that, we bubble air into it. It's a level probe that we call a bubbler. We end up putting about 7/10 of a liter of air into the mercury layer every minute. And when you do that, it makes mercury bubbles, which is kind of cool. They're really pretty, and I'll show you a video of it. But what it does is the mercury coating the bubble is now, instead of having a density of 13.6, is very buoyant and floats. And you can imagine it's going to overflow the weir of the decanter and leave. So it can also, these little tiny droplets of mercury, they want to be together, right? So they form a raft and they float on the top of the water. So even though you've got liquid that's got a density of 13.6, it floats on top of water and it'll stay there for a really long time. And then when these bubbles burst, these mercury bubbles burst, it forms lots of really small droplets. So if you look at the video when I started up here, watch the bubbles as it splashes, as it oh, you can't see it because I don't have the video. I'm sorry. It's a PDF. So just imagine this is a mercury bubble. It's instead of what you're seeing now is the water bubble. It's a water bubble coating the air. If you had mercury, it would completely coat this. So it'd be nice, silvery, mercury-looking bubble. And when it breaks, it just throws mercury all over the place. So let's talk a little bit about the nature of mercury. I told you I really want just a pool of mercury at the bottom of the vessel. What I really get is something that looks like this, where there's lots of droplets of mercury. This is a small, about a 15 ml tube. So the very bottom of this is probably a couple milliliters. So these are pretty small droplets you're seeing here. And because the decanter is bubbled, it's really constantly stirred up, and these bubbles keep forming. And it agglomerates different at different temperatures, at different pHs. You obviously don't want agitation, and you want as much time as you can in the decanter. That's what's really important if you're going to ever separate it. So we'll talk a little bit about the condenser. The thing on the right is a picture of the mercury decanter. On the left, it talks about how the condensing happens. The condenser sits right above the mercury water wash tank, and the liquid drops into the decanter. The decanter itself was undersized. It was improperly designed before it was built. And so the vapor exiting the decanter is about 70 degrees C, which is really hot for a decanter. We're designing for something way less than 50 degrees C. So what's coming into the decanter is really hot. which is really good for agglomerating because the hotter it is, the faster it agglomerates. But you also have really hot nitric acid solution in the decanter now. And if you have really small droplets, they're easily dissolvable with this nitric acid. And of course, you have the air bubbling in there also. So what we found is the mercury seems to be collecting in this condensate tank. And that's what I have a picture on the right. The really big tank is the condensate tank. And you can see it's quite a bit bigger. It's 4 times the diameter of the mercury decanter. And what that does is the mercury decanter itself has a residence time of about 7 to 10 minutes, whereas the condensate tank has a residence time of about a half a day. So it's a lot more time for the mercury to agglomerate and settle. You know, it's 100 times the volume. It's 200 times the residence time. It's also, the one thing bad about it is we purposely chill it. And because it's chilled, it doesn't agglomerate quite as fast, but the other factors make a much bigger difference. We'll talk about some of the other process factors. I told you that the ammonia scrubber actually caused problems, and I have a picture of the ammonia scrubber on the right, and the red arrows are pointing to all the mercury droplets that the ammonia scrubber filtered out. And this was just in one experiment. So you could imagine if you ran this over and over again, there'd be lots of mercury that would accumulate in the ammonia scrubber. As a matter of fact, right now, even though the ammonia scrubber hasn't been operated for the last 6 years, they're removing the basket that has the Interlox saddle packing in it. They're going to move it and putting it into a nitric acid solution to dissolve up the mercury because of the differential pressure across the scrubber has gotten too high, and they can't pull a vacuum in the tank anymore. So in addition to this, the scrubbers, all the tanks have bubblers, and it's the biggest problem in the mercury decanter because it's such a small vessel. And then this condensate tank has a sparge ring in it, which is designed to give you a little bit of mixing into the condensate tank. Luckily, it's been turned off for the past 10 years, so it hasn't caused any problems there. And there's a couple other process factors. I told you that there's a nitric acid solution as you boil, as you strip off the nitric or the mercury. You always have about a pH 2 nitric acid solution. That's the 620 ppm that you see there, 0.01 molar nitric acid. And it's really good at dissolving mercury. And so one of the things we did is a lot of tests at different pHs. And you can see the test we did at the lowest pH at pH 2, which is where we are. You can see the yellow mercury nitrate that's being formed. And as you said, it just more and more of it forms, and you slowly dissolve up the mercury and lose it. It ends up going into the condensate. Then you have to process it at a later date. You can see when we raise the pH just up a little bit, this is a really nice looking mercury. It hasn't agglomerated perfectly, but this is way better than the mercury in those other vessels. If you raise the pH even higher, even at pH 10, it looks like you're oxidizing it. You're making some black mercury oxide, mercury +1 oxide, so it's Hg2O. And then as the pH is raised higher and higher, it happens faster and faster, and you convert all the elemental mercury into an oxide. And that's the last thing you want to do. You want elemental mercury so you can pump it out and get rid of it. Once you form some other kind of mercury, you're going to lose it and may never recover it again. So, but one of the things we found when we were doing this is ionic strength makes a big difference. If you could go to a really low pH for a really short time, it agglomerates really fast. So at pH 12, it agglomerates really fast. So we did some testing where instead of using the acid or the base to control the pH, we added a sodium nitrate to it to bring the ionic strength up. And we found that we got just as good a agglomeration as we did at, going to the same ionic strength just with an acid or a base. And so one of the thoughts was maybe you run the decanter or the mercury, the condensate collection tank at a neutral pH and add some kind of salt to it. I was thinking sodium nitrite might be a better salt because they're going to add it in the next tank anyway. So, but if you get the ionic strength up, it agglomerates really fast. The mercury looks great. You don't oxidize it. You don't dissolve it, and we'll be able to recover it. So where do we go from here? The big thing for us is if you can't pump the mercury out, you just give it time for something to go bad. So they need to buy new pumps. We'd like to do some ionic strength tests and some bubbler tests, but they aren't funded this fiscal year, so we probably won't do those until October of 2026 at the earliest. And what we're recommending is some tests where we just change the pH and the ionic strength and see if we can find that sweet spot where we agglomerate the mercury really quickly, so that we send as little back to the recycle system as we can, so we don't have to process it again. So the recommendation is to finish our experiments, build and implement the new mercury pumps, and then move forward with the better processing conditions so we can finish processing the radioactive waste. I had a lot of help on this with a lot of people. I don't do research anymore. People do it for me. So Alex Nikoloff at the Institute of Technology, he's the one that helped me develop the new anaphone. Did a lot of experiments for me at trying to understand how ionic strength could help you coalesce this material faster. And then some of the researchers in my group, Sean Noble, Matthew Siegfried, Matt Williams, Anthony Howe, Catherine Miles, Nathan Morgan, all did great work in doing experiments to try to better understand the mercury recovery. And we have a really good relationship with the other company that actually runs the defense waste processing facility, and especially with Terry Fellinger, Kayla Lambert, and Bill Holscheider. And it's just a coincidence Kayla isn't actually related to me, even if I call her cousin Kayla when I see her. So, but I wanted to thank all those people and a whole lot more that have helped me with these experiments. So if you do have any questions, I'd be happy to answer them. And the questions don't have to be about mercury or radioactive waste processing. If there's something else you'd like to talk about, I'd be happy to answer them too. And I didn't say this, but at the very beginning, I said I've spent a lot of work in supporting AICHE. So for those of you that are chemical engineers, you probably know what I'm talking about. If you don't, it's the American Institute of Chemical Engineers. But I think it's really important as we go through our careers to do something to help our profession. And one of the big things I do is my support of my local section and the nuclear engineering division and things like that within AICHE. I think it's really good for me, but now that I've gotten later in my career, I think I don't do it for me anymore. I do it mostly for other people like you guys. So if there's anything I can do, if there's questions you have, I'm going to go back to my cover slide. And I'm going to do that because I want you to have my second slide, which has my contact information. If you ever need to, if you have a question or you want to send me an email, you're free to do it at any time. I'd be happy to answer your question. So even if you don't have a question today, or you don't want to answer it, ask it in front of a group. Just give me a call or send me an email. But thank you so much for listening to me, and I really apologize for it being so difficult at the part. You would have loved my videos, by the way.
Thank you, Dan. Thank you for a great talk.
Thank you, guys.
I think
Sure.
Mr. Brown has a question.
Hey, Dan, great talk. Good seeing you again.
Good seeing
So,
you too, Kevin.
yeah, I think, making the point that you got rid of this is more of a comment. Getting rid of 3 flammable gases and formic acid is a huge deal in anyone's world, especially when you're working with fun stuff like nuclear tank waste.
Exactly.
So that was a big deal. I do remember those days. A comment or something I'd like you to comment on. We did about 10 years of piloting of this facility at what we called the IDMS back in the day. And the differences between what we saw in the pilot facility in terms of mercury removal and what you actually got. I don't know if you'd like to, maybe you don't want to comment on that. That's up to you, but it seems to me that there were some fairly stark differences between the piloting and what you guys actually saw. I shouldn't say we, I'm not there anymore. What you saw in the DOPF. Thanks again, Dan.
Yeah, thanks, Kevin. That's a real good question. So in the pilot facility, we had a 1/5 scale DWPF pilot facility, what was Kevin was talking about. And it had the same equipment that DWPF had. The one thing that wasn't scaled was the mercury decanter. So only in the last few batches that we ever did was the mercury decanter replaced with the best scale you could do. And then we processed a couple of batches. The worst batches we did in that pilot facility were the last 3 that had that mercury decanter. In those last 3 batches, we all had major foam overs. The antifoam was terrible. We knew that in the pilot facility. But because of the foam overs, it contaminated the mercury water wash tank, which was a decanter. So it made it impossible for us to do a really good mercury balance for the run. So we just said, oh, I think it was okay, as opposed to we know exactly what it was. When DWPF went to do their radioactive or their non-radioactive startup, so they did 19 batches in DWPF with cold chemicals, non-radioactive chemicals before they started up. In those first 17 batches, everything worked perfectly. I mean, it worked great. In batch 18 and 19, they actually added mercury to the facility. And in those 2 batches, they had all kinds of problems. They foamed over. It was the worst 2 batches they did. So I think the answer, Kevin, is if we had known what we did by the time we started up DWPF, we would have done things very differently in the pilot facility. And we probably didn't listen to they were so busy wanting to start up DWPF that they didn't want to put effort into things that were important. They thought they could figure out how to do it on the fly. And so it took them a lot of years of processing to figure out how to process efficiently. But I think you're right, Kevin. The changes that we've made with the glycolic flow sheet and the new antifoam are real game changers and are going to make the processing a lot better.
Thanks, Dan.
Hope that's not too much information, but I thought it was a good question. So
there is another question from Rachel.
I have a question. So you mentioned adding a sodium nitrate to the mercury to help it clump together better and not like disperse into these tiny bubbles. Would that possibly introduce another problem where if the mercury like kind of clumps together, it's trapping water inside of itself and that would make it a little bit more buoyant? Or is we hoping that the clump or the size of the mercury chunks that are coming together are big enough that it's going to overcome that buoyant force?
Yeah, so the hope here is if the ionic strength is small, you don't form an emulsion, and that's really emulsion is a dispersion of a liquid in a liquid. So the mercury droplets are very well distributed through all the water, and that's the problem. You want to bring them back together. So at really high ionic strength, it breaks that emulsion, and so these mercury droplets actually come together. And that's what the whatever salt that you're adding to it is going to do. By increasing the ionic strength, you break that emulsion, you get big droplets. Once you get the big droplets to form, the big droplets hit each other, become bigger droplets, and they're going to fall to the bottom of the decanter because of their density. So in all the tests that we've done so far, it's looked really, really good to increase the ionic strength. And the question really is, what salt would you add that wouldn't cause a problem? Because, and anytime I talk to people, I can solve anybody's chemical solution, but any chemical solution I come up with to solve your processing problem is probably going to cause another processing problem. And that's been true with everything I've seen through the years. And even with the glycolic flow sheet, we added the glycolic acid to keep from generating hydrogen, hydrogen being a flammable gas, right? If you take glycolic acid in the condensate and you put it into a high level waste evaporator at 160 degrees C, it still forms hydrogen. So even what seems like the most perfect solution probably is going to cause another problem. So that's what concern I always caution people before they make too many changes, is that you really have to study them a lot to make sure that you understand it well enough not to screw something else up.
The next question is from Haruko.
Hi, thank you so much for our great presentation. I'm really sorry that I missed the first part of the your presentation. The current Purex process doesn't have mercury in the process, I believe. What was the original reason mercury was in the high level waste, or didn't the previous generation, did they expect this sort of process, and why did they need to use mercury in the first place?
Okay, so the site reactors at the Savannah River site were heavy water reactors, and they were aluminum clad reactors. So the fuel and the targets in the reactor, and the fuel would be, of course, what generated the neutrons. The targets were the lithium and the say the uranium-238 or whatever they're trying to add neutrons to make the plutonium they want, right? So it's aluminum clad. Mercury is a really good corrosion agent for aluminum. As a matter of fact, what they did is they co-extruded the U-235 with the aluminum, and it was just really hard. It's not like you can just rip off the outside like a can, like you do in some assemblies. Since you co-extruded them, the only way to get to them was to dissolve everything. And so they used a nitric acid solution with mercury as a catalyst to dissolve up the aluminum so they could recover all the uranium that they wanted from, the plutonium they wanted for the nuclear weapons or any other isotope they might have been producing in the reactor. So yeah, that was a really good question. And
mercury.
I had meant to mention that, and it was actually a note in my PowerPoint, but when I went to the PDF, I forgot to mention that. So thank you.
That the mercury was added the first step of the separation process.
Yeah, there were two different canyons, and they actually had two different. One had what we called a Purex process, and the other we called H-modified Purex, which was they started up the F canyon first and the H canyon later. But because of one of them just handled the extruded fuel, it had a lot more mercury in the waste. And that's the waste that we're processing now. It's the H canyon modified Purex process that had all the much higher concentrations of mercury in it. So if any of you are looking at the Hanford facility, there's a lot less mercury there. They never put much mercury in the processing, so they don't have the same issues that the Savannah River site does.
Yeah, it's almost more of an impurity at Hanford than it is anything else, according to their people.
Thank you. Thank you for the answer. Thank you.
The next question is from Tracy.
Hello. A quick question. So I know adding nitric acid to mercury was being discussed, but I was also wondering if it's just being added as like a liquid or maybe being bubbled through. Could it be like an option that the temperature is high enough that you pretty much like insert nitric acid as like a gas form, and then you don't have to worry about, water being formed? So for example, if you have it high past 100 degrees Celsius, then I know water was being discussed, and you could probably take that out at the same time.
Yeah, it's a good question. So all the processing we do is aqueous based.
Okay.
So we're always boiling around 102 C. There's enough salts there, so it raises the pressure. So unless we boiled off all the water, we'd never go above 102 C. One of the problems is that we have a lot of nitrate and nitrite in the waste coming in that we process. And so when we go through our processing, we add acids to it, both nitric and glycolic acid to it. And what that does is it takes the nitrite and destroys it. A lot of the nitrite forms NO. NO gets oxidized to NO2, and then NO2 gets scrubbed by water to make nitric acid. So no matter what we do, we always have an acidic condensate that's being processed, and that's where we're worried about. There's the one thing that I tried to convince the plant to do about a year ago was I did some experiments where I convinced them to allow me to do one inert experiment. So we put nitrogen in instead of air as a dilution gas for any flammable gases that we might make. By putting in nitrogen, there's no oxygen anymore. And what we found is that, and we knew this all along, NO gets oxidized to NO2, NO2 gets scrubbed by water. But if you don't have any oxygen, then the NO2 doesn't get scrubbed by the water. So you don't make nitric acid, and the condensate is really clean. And it really does help the mercury. You lose less of it by dissolving it. So, but they think that's a crazy idea and they'll never do it. So it's also really hard when you're processing under a vacuum. You have to have a really leak tight vessel to make it inert process. So especially now that it's a 30-year-old facility, it's just, they don't think it's a practical thing to do. Although it would really help if they did it. So
Thank you.
thanks for your question.
Any other questions from the audience?
Any non-technical questions?
All right. I guess we can wrap up. Thank you so much, Dan, for sharing your experience, and thanks everyone for the insightful questions. And please keep an eye on your inbox for the next seminar. Thank you.
Thanks again, Dan.
Welcome.
Thank you, Dan.
You're welcome.
Thank
Thank you,
you.
everybody, for
Yeah,
for
thank you.
listening. Have a great day.
Thank you. Have a good day
Take
as
care.
well.